Hello everyone, I'm Norman Wildberger and we're here at the University of New South Wales. Today I want to extend our discussion of the curvature of the parabola from the y equals ax squared case to the more general case. And our motivation for this is the following, that when we have a curve in the plane, then at a given point we can talk about the tangent line, and that's unique. There's only one tangent line. When we talk about tangent conics to a curve, we're talking about a conic which agrees with the curve up to degree 2. And in general, we can expect that there will be quite a lot of different conics that have that same amount of coincidence with the curve at that point. So we can see that by thinking about the space of all conics. The space of conics is 5-dimensional. It's 5-dimensional because to specify a conic requires 6 coefficients, and those coefficients are adjustable up to a scale. Or another way of thinking about it is because the conic is associated to a 3 by 3 symmetric matrix up to a scale, and then again there's 6 minus 1 equals 5 degrees of freedom. Another way of thinking about that is that a conic is generally specified by 5 points. So it's a well-known fact of geometry that 5 points determine uniquely a conic. So when we have a curve, C, and a point, let's say P on it, to ask that a line goes through that point and is tangent to it is 2 conditions which specifies the line precisely. But when we're talking about a conic that passes through that point and is tangent to this tangent line at that point and has the same meeting degree as the curve, then we have a 2-dimensional space of possibilities. So there's more than one tangent conic. Okay? That means we have a bit of freedom in choosing a tangent conic in general. The method that we've talked about so far, when I introduced the tangent conic officially, via the process of Lagrange and making calculations with x plus r and y plus s, that resulted in a particular conic. But that was only one of the number of possibilities. Another possibility is to look at the osculating circle, which we get by taking 3 points and looking at the circle that goes through those 3. And then taking the limiting value as these points approach the given point. That's the idea that goes back to Huygens and Newton. Right? That defines the original definition of the center of curvature, is the center of that limiting circle. Okay, so the problem with the circle, the oscillating circle approach, is that when we go to higher dimensions, it does not generalize very easily. So for example, when we go to surfaces and we have a point on a surface and we ask what's the oscillating sphere, it turns out that there is no unique oscillating sphere. You cannot go up in dimensions by considering 4 points on a surface and allowing them to go to a point. The sphere that you get will depend on the way you choose the 4 points. So generalizing a circle is difficult. For that reason, we're going to take a very parabolic approach. This is a somewhat non-standard approach to curvature. And in fact, the place where I first learned about this parabolic approach that I'm going to talk to you about today is in a paper of Zvi Harel, who's a mathematician at the Technion in Israel, who wrote a paper called Curvature of Curves and Surfaces, a Parabolic Approach. And we're going to sort of follow his suggestion, although we're going to be doing things a little bit differently than he did. But if you're interested in this approach, I recommend this paper, which you can find on the internet. It's from 1995. Okay, so let me remind you that last time we looked at the situation of a standard parabola where we had the curve y equals ax squared. And we saw that that thing had a focus. Focus was at the point 0, 1 over 4a. And exactly twice as far away is the center of curvature. So that'll be 0, 1 over 2a. And the radius of curvature is then 1 over 2a. And the curvature itself, usually called, say, r, and the curvature itself is defined to be 1 over r, and it's usually called k. And so that'll just be 2a. All right, so what we're interested in doing is finding analogs of these kind of formulas for a general parabola. So we need analogs for a general parabola. Because our strategy is going to be the following, that if we have a curve in space, there's some curve, then we're going to be interested in some particular point, tangent line. We're going to look for the parabola, which is tangent to this tangent line and has a vertex there, and which best approximates the curve at that point. So in other words, so that the axis of the parabola is perpendicular to the tangent line. We're going to look for this special parabola, and where its focus is going to be then the point that will orient us in the same way that this point F was orienting us in the standard position. So we have to look at parabolas a little bit more generally, and we find that when we do this, some new things appear, and we have to enlarge our view a little bit from this case here. This turns out to be rather a special case that's a little bit too special for some reasons. All right, so what I'm going to do is I'm going to look at this parabola, the general parabola, in two different ways. So the first approach is going to be a projective view. Projective view of a general parabola. So what is the projective view of a general parabola? Well, it's simply this, that if this is the projective plane with its line at infinity, which we're usually denoting 0, 0, 1, then a parabola is, or can be defined to simply be a conic which is tangent to the line at infinity. So you choose any point on the line infinity, and you choose any conic which is tangent to the line infinity at that point. You can define a parabola to be such a conic. That's the projective definition, or maybe one could say an affine definition of what a parabola is. So we can define a parabola as a conic tangent to this line at infinity, 0, 0, 1. But to make life simpler for us, we're also going to want this conic to go through a special point, because in practice we want to actually be going through a particular point on a curve. And so for that we're going to want to impose another condition. We're going to look at those parabolas which also pass through the origin and have their vertex there. So we want this to be the vertex of the parabola. And what its orientation is, we don't care. That can be any line. And then its axis will be in this direction here. And so we'll get a parabola that looks like this. And of course, eventually, projectively, it goes and it meets the point at the line at infinity at this point up here. So let's put some numbers to this. Let's suppose that this tangent line happens to be the line Lx plus my equals 0. Projectively, that's the line Lm0. This point down here, the origin, is just the point with projective coordinates 0, 0, 1. This vector here will be the perpendicular vector to this line, so it will be the vector L, comma m. And so the point at infinity on that line will be the point whose coordinates are L, m, and 0. It's the point at infinity on the line with direction Lm. And the line at infinity, we know, is our line 0, 0, 1. The other thing that's involved in the description of the conic is the actual matrix for it, and we'll let that be A, B, C, D, D, F, F, G, and G. So that's the matrix for our parabola P. Another way to think about it is if you choose a point that's far out here, a point that's far out would be, say, TL, TM1, if I multiply by big number T. And then this is the same as LT, LM, and 1 over T. And then if I think about what happens as T gets very big, then this will approach 0, and we're moving towards the point at infinity. All right, so let's have a look at the two conditions that we want to have satisfied. The first condition is that the tangent at 0, 0, 1 is, well, we know how to get the tangent of a conic at a point. What we do is we take the matrix for the conic times the transpose of the point. When we do that, we just multiply by that matrix there. We're going to pick up the last column, which is F, G, and C. And what we are told is that that should be the line LM0. So that's a condition, that's the projective condition on the matrix to ensure that its tangent line at this point 0, 0, 1 is indeed the line Lx plus my equals 0. And the other condition is that the tangent at our point at infinity, Lm0, well, that is, first of all, it's A times Lm0. So that's going to be the column AL plus DM, DL plus BM, and FL plus GM. that tangent at that point infinity ought to be the line at infinity. The line at infinity has equation 0, 0, 1. So if we put these two conditions together, we find that the matrix A has to have the form A, D, D, B. And now we can just replace the last column with L, M, and 0, and the last row with L, M, and 0, with the additional conditions that AL plus DM equals 0, and DL plus BM equals 0. So any matrix that has this form will represent a parabola which has a vertex at the origin and is tangent to the line at infinity. That's our definition of a parabola. Well, let's suppose that, to make some additional computations, let's suppose that L, M are both non-zero, so that our tangent line is neither horizontal nor vertical. In that case, we can solve for, say, A in terms of D, M, and L, and we can solve for B in terms of D, L, and M. And then the matrix A can be rewritten as, well, after I put these things in and then sort of clear fractions, minus dm squared, dlm, L squared m, dlm, minus dl squared, m squared L, L squared m squared L, and 0. And so the associated quadratic form or associated equation for the conic will be minus dm squared times x squared plus minus dl squared times y squared plus 0 times z squared plus 2dlm xy plus 2l squared m xz plus 2 m squared L yz equals 0. And then if you set z equals 1 to get a planar curve, or replace capital X over z with little x and capital Y over z with little y, then you can check that the conic that you get can be written as the equation d times mx minus ly squared equals 2lm lx plus my. So this is a general equation of a parabola which is tangent to this line Lx plus my equals 0 and has a vertex right here so that the axis is perpendicular. And you can see there's a certain amount of freedom. Of course, we can scale m and l, but we can also scale d. And if we scale d, then we can get the various different shapes of parabolas opening up more narrowly or more widely. This is kind of an interesting formula for the parabola. It's not so different from y equals x squared. If you think what happens when Lm equals the vector 0, 1, Well, then our assumption doesn't hold because L and M are not both 0. So this derivation is not actually completely valid. But if you sort of think about this as just being a constant incorporated into this constant, you can see that it's roughly the same, that this would be y and this would be x squared. So y equals some constant times x squared. But strictly speaking, this derivation doesn't hold for this particular case because we assume that L and M were both non-zero because we divided by L and M during the process. I might say a little bit about the meaning of this, just some geometrical meaning here. So if our point x on the parabola has coordinates x and y, then these two quantities that are involved, the Lx plus My, is really the dot product between this vector, here's the vector Lm, and this vector xy. So the dot product between these two vectors is on the right-hand side. And on the left-hand side, this term mx minus Ly is really a determinant. It's a determinant formed by the two vectors, Lm and xy, all squared. And so it represents an area of a parallelogram. So it's telling us that in a parabola there's some relationship between this kind of area, this area squared, is linearly related to the dot product between this vector and this fixed normal vector. All right, so that's one view of a parabola. That's a kind of projective view of a parabola where we've just used some projective geometry and the two conditions to determine the formula for it. Okay, but now I'd like to turn to another aspect, but before I do that, let me give you a problem to think about, which is related or gives you more practice in figuring out what points on a conic have what tangents. So the problem has two parts. So for the conic C, let's say, you're given by 18 plus 4x minus 23y minus x squared plus xy plus 5y squared equals 0. Define the associated matrix. Compute the tangents at 2 points, A, which is 1, 3, and B, which is the point 4, 2. So let's say using projective geometry. Compute the meets of these tangents. And show this is the polar line the polar point, let's say the pole, okay, the pole of AB with respect to the conic C. So the story there is we've got some conic. It doesn't look like this, but let's say it does. We have 2 points A and B on it. We need to find the equations of the tangents. We need to find where these tangents meet, or let's call it M. And then we want to compare this point with this line AB, which is the join of the 2 points, and just convince ourselves that this is the pole of this line with respect to the conic. And here's the second part of this problem. Where, if anywhere, does the conic C meet the line at infinity. Okay, it won't meet the line at infinity if it's an ellipse like this, but suggesting that it's probably a hyperbola. So it's a hyperbola that meets the conic, the line at infinity at some point, and show that the asymptotes, show that the tangents at these points are the asymptotes to C, asymptotes of the curve, and show that their meet is the center of the curve. That's an important fact about hyperbolas, that if you take the tangents to where the hyperbola meets the line of infinity, that those are the asymptotes. And where they meet is the center of the conic. Okay, so now I'm going to introduce, we're going to make some computations with foci and directrices. So the focus directrix definition of a parabola. We'll see if this projective view really does correspond to our more familiar focus directrix point of view to a parabola. And we want to actually get some concrete formulas, and these concrete formulas are going to be really important for us in our work with curvature. All right, so we're going to assume that our parabola P has vertex 0, 0 as before, and we'll assume its focus now is at point capital F with coordinates little f and little g. So same kind of story before. We have some parabola, which has got its vertex right here, and it's got a focus here somewhere at the point FG. Okay, then the directrix is well, it's going to be a line that's equal amount on the other side of the vertex and parallel to this tangent. Let's draw it here like this. So there will be the directrix, let's call it L. And what's the equation of this line? Well, it has perpendicular vector FG, so its equation has to be f of x plus gy equals something. And it's got to go through this point here, which is the point minus f minus g, because we want the vertex to be equidistant from here to here because of the condition of the parabola, that the quadrants to the point is equal to the quadrants to the line. All right, and if we know that this line goes through this point, then we have to add f squared plus g squared equals 0. That's the equation of the directrix. And what's the equation of the parabola? If we have a point x on it, the metric definition of the parabola is that the quadrants from x to f equals the quadrants from x to this line L, where quadrants is, as usual, the square of the distance. So let's have a look what this equation looks like. Okay, so the quadrants from x to f, let's see what x is first. It's the point x, y. We're working in the Cartesian, ordinary Euclidean geometry here. now. So we're just taking the quadrants between x and f first. That's x minus f squared plus y minus g squared. And that ought to be the quadrants from the point to the line. So how do we calculate the quadrants of a point to a line? So that's this perpendicular quadrants here. If you know a point and you know the equation of a line, how do you find the distance between them? Or better yet, how do you find the quadrants between them? The formula is that you take the equation of the line and substitute the point. So fx plus gy plus f squared plus g squared. And you have to divide by f squared plus g squared and square that. If you were taking a distance, you would take the square root of all that. And then there would just be it wouldn't be a square here, there would be a square root in the bottom. That's a familiar formula. This is a clearly superior formula because it doesn't have any square roots, of course. It has, the content is exactly the same. Okay, we have to now see what this equation looks like. So let's multiply it out. F squared plus g squared times. Here we get x squared minus 2xf plus f squared plus y squared minus 2yg plus g squared. And on the other side, we get, when we square the top, we're going to get, I'll think of it like two terms. The square of the first term is f squared x squared plus 2f gxy plus g squared y squared. Twice the product will be 2f squared plus g squared times fx plus gy. And then finally the last term squared, f squared plus g squared squared. Okay, we have to simplify this. Well, it's not so bad because this term here, this f squared plus g squared squared, also appears on this side. It appears when we take f squared plus g squared and multiplied by this f squared plus that g squared. So they're going to cancel. When we bring all the x squareds to one side, here we have x squared times f squared plus g squared, and here we have f squared. So when we bring it to the other side, we're going to get g squared times x squared. The terms involving x and y, there's only this term. When we bring that to the other side, there will be a minus 2fgxy. And the y squared terms, when we bring them all onto this side here, right now there's f squared plus g squared times y squared, and then here there's a g squared, so we subtract that, we'll only get plus f squared y squared for the quadratic terms. And the remaining terms are these ones here and the ones that we already have there. And there's an f squared plus g squared common factor. And here you see that you're getting 2 times xf and yg. It's exactly the same thing as here, but with a minus sign. So when we bring it to the other side, we get 4 times f squared plus g squared times fx plus gy. And pleasantly, this is a square. So this is actually gx minus fy all squared. And so we get, for the formula for the parabola, this reasonably pleasant expression. There's a formula for the parabola with vertex at 0, 0, and whose focus is at fg. So it reads gx minus fy all squared on the left-hand side equals 4f squared plus g squared times fx plus gy. Okay, so what we'd like to do now is have a look at that formula near the origin. So we want to ask, what does this look like near the origin as a function of x. In other words, if we just had a look near here and thought of that as a function of x, what does that function look like? Well, one way would be to solve for y. But we're going to do that in a more efficient, a more algebraic way, without having to solve a quadratic equation, by an important idea, again going back to Lagrange, that basically what we're really interested in here is we're looking at the tangent conic situation. So we're interested only in terms of degree 2 or less at the point 0, 0. We're only interested in degree 2 or less, meaning we can ignore x cubed, x to the fourth, and higher terms. So what we're going to do is we're going to ignore x cubed, x to the fourth terms, and so on, and we'll just let our function that we're looking for be alpha x plus beta x squared. And there might be some other terms, but we're going to ignore them. So what we're going to do is we're going to plug that into the formula and solve for alpha and beta. It's a way of solving for y without having to, if you've forgotten the formula for the quadratic. Okay, so let's plug it in. So gx minus f, we're saying y is equal to alpha x plus beta x squared. So we'll just substitute it in. So there's the left-hand side of the equation. And on the right-hand side, 4f squared plus g squared times fx plus g, y again replaced with alpha x plus beta x squared. Okay, on both sides, we're just going to look at the coefficients of x. Where do we find x's? On the left-hand side, there are 0 x's because it's all squared. On the right-hand side, the only place we see x is right here and here. So there's an f plus g alpha. So the coefficient is f plus g alpha. What about the coefficients of x squared? Well, on the left-hand side, how are we going to get an x squared? We're going to get an x squared by squaring this term. So the square of this term would be g squared. And if we take minus twice the product, we'll get an x squared term. So minus 2gf times alpha. And if we square this thing here, we're going to get an x squared term with coefficient f squared alpha squared. And on the right-hand side, where's the coefficient of x squared? There's only one right here. So the coefficient is 4f squared plus g squared times g times beta. Well, this can be rewritten pleasantly as g minus f alpha all squared. And I guess maybe I should say from the first one, we can immediately say what alpha is. Alpha is going to be equal to minus f over g. And so when we rewrite this second one, first of all, we just observe this thing is a perfect square. It's this thing here. And then we know what alpha is. So if we put alpha in as minus f over g, then the minuses give us a plus, and we're going to get f squared plus g squared all over g squared. We have to square it. And that's equal to 4f squared plus g squared times g beta, telling us that beta equals f squared plus g squared over 4g cubed. All right, so what have we done? So we've shown that if we have a parabola, vertex at the origin, focus at the point fg, then when we look at that parabola near the origin, it's equal to a function, alpha x plus beta x squared. And the coefficients of the alpha and beta are given exactly by these expressions in terms of the entries of the focus, in terms of f and g. So if we know f and g, we can write down these formulas, and we know what the parabola looks like near the 0, 0. Pleasantly, these two formulas, let's give them names, 1 and 2. Pleasantly, these can be inverted. This is not at all obvious, but when you stare at it for a minute, you see that it's true. 1 and 2 can be inverted. In other words, we can solve for f and g in terms of alpha and beta. How do we do that? Well, I'll write down the formula. It's minus alpha, 1 plus alpha squared all over 4 beta. And g is 1 plus alpha squared over 4 beta. Where does that come from? Here's what I think what we do. We look at this equation here first. Look at 1 plus alpha squared. 1 plus alpha squared, so if we take that, it will be 1 plus f squared over g squared. So that's f squared plus g squared over g squared. And when you divide it by 4 beta, the 4 f squared plus g squareds cancel, and you just get a single g. Okay. So what I'm saying is that 1 plus alpha squared equals 1 plus f squared over g squared. So that's f squared plus g squared over g squared. That's what the numerator is. And then if you look at beta, what beta is, if you divide that by beta, then the f squareds plus g squareds will cancel, and conveniently the g squareds will cancel, and you just have a 4g. So that allows you to calculate g. And once you've calculated g, then f is just minus alpha times that. Right, so what is this telling us? That's telling us that if we have a function that's going through the origin, any function, let's say it's y equals 2x plus 5x squared, and maybe it has higher order terms. And we want to know, well, what's the normal parabola that's approximating that function at the origin? Where is its focus? Where is f and g? These formulas tell us that all we have to do is we have to think of these two constants, alpha and beta, and we write f equals minus 2 over 1 plus 4 all over 4 times beta over 20. So that would be 5 to 1 minus a half, I suppose. And g would then be that same thing divided by minus 2. So maybe a quarter. That would tell you exactly where the focus is. All right? Got a function. Immediately you know where the focus of the associated normal parabola is. Okay, what about curvature? Let's write down what the curvature is. The curvature What's the curvature? Well, it's easier to talk about the radius of the curvature. So there's the focus. Remember that for the parabola in the standard form, the center of curvature was exactly twice up here. So if this is the point FG, then the center of curvature will be the point 2F, 2G. So the quadrants of curvature is just the quadrants between C and O. That will be 4 times F squared plus G squared. So as an exercise, you might like to calculate what this is. In terms of alpha and beta. Notice that we're getting the quadrants of the curvature and not the radius. If we want the radius of curvature, we have to take the square root. So let's give this a name. Let's call it R for sort of quadrants of the curvature. And then the radius of curvature would be equal to the square root of R, which is, let's say, little r. But for a general parabola, this square root may not be inside the rational numbers or whatever field we're working over. This is a transcendental thing that's taking us outside of whatever field we're in. With these quadrants of curvature, we're just right still in the algebraic framework of whatever field we're working over, which could even be a finite field. So everything that I'm saying here works over a finite field, or say the complex numbers, just as it does for the rationals. All right, so next time we're going to have a review of these very important formulas and show how this allows us to get curvatures for general curves at general points, and we'll make some explicit computations to show you the power of these relatively simple but pleasant formulas. So I'll see you then.